is finding a basis in which the matrix representation of an operator is diagonal. That means off diagonal elements will be 0. In the last discussion we have seen if we have a basis, we have some matrix representation. To change your basis, the matrix will be different. Now we are asking a question, for which basis the matrix will be diagonal. So identifying a basis in which the matrix is diagonal is actually diagonalization. So diagonalization basically is finding a basis for which so diagonalization implies find the basis in which matrix is diagonal. Find the basis in which matrix is diagonal. Now, when can the matrix be diagonal? If I say I have a basis B1, A, B1, B1, A, B2, B2, A, B1, B2, A, B2. Now this basis that we are yet to find can be assumed to be orthogonal basis, also orthonormal basis. So we can say that this basis can be found in such a way that Bi, Bj can be equal to delta I. Even if we are not finding a basis like that, the basis can be written in that way using Grom's-Smith orthogonalization procedure. If we find a basis which is not orthogonal, we can always orthogonalize that. Now, in general, if this basis, so what I want is, I must choose my B1 such that there should be a value here, and there should be 0 here, there should be 0 here, and there should be a value here. And because of this condition, the basis should be having the following properties. The basis should have the properties. If this equation has to be satisfied, I must have the property that A of B1 should be equal to lambda 1 times B2. A of B2 should be equal to lambda 2 times B2. If any vector satisfies this kind of relation, we call this an eigenvector of A. We call this an eigenvector of A, and this is called an eigenvalue of A. So, the basis in which the matrix is diagonal are essentially eigenvectors of the matrix. And the diagonal elements will be eigenvalues of the matrix. So, lambda 1, lambda 2 will be eigenvalues of the matrix, B1, B2 are eigenvectors of the matrix. So, if you can find eigenvectors of the matrix, then you can say that. So when you write down this matrix, the eigenvector matrix, you know that you can make a transformation of the basis of the matrix A to a similarity transformation. Correct? So now let me say that I have some. Okay. So now let us formally write it in the following fashion. So let's say that A of B1 is equal to lambda 1 of B2. So if I write this as an identity matrix here, with no loss of generality, this essentially means A lambda I B1 is equal to 0. So if this is basically 0 vector. So if I want a non-zero eigenvector to be present here, then the determinant of this has to be equal to 0. So condition for finding the eigenvalues of a matrix is given by A minus lambda. A minus lambda I is equal to 0. So determinant of A minus lambda is equal to 0 gives you a polynomial with lambda. Gives polynomial of order n if A is n by n matrix. This polynomial is called a characteristic equation. So this polynomial so I can simply say A minus lambda I determinant is equal to 0 is called characteristic equation. It's called characteristic. It's a polynomial in lambda and you have n roots. It's an nth order polynomial equal to 0. You have n roots of the characteristic equation. The roots of characteristic equations are called eigenvalues because those are the values of lambda that will satisfy this equation. Okay? So roots of characteristic equation are eigenvalues. We'll come back to this problem. So, if you have this characteristic equation, A minus lambda I, determinant is equal to 0, if you put lambda equal to A, then what happens? It satisfies this equation because A minus A into I is equal to 0. So, every matrix satisfies its characteristic equation. Every matrix satisfies its characteristic equation. This statement is what is called Cayley-Hamilton theorem. Cayley-Hamilton theorem states that every matrix satisfies its characteristic equation. There is no proof required, it is obvious. You put lambda equal to A, it will be satisfied. Determinant of a zero matrix is 0. Now, the problem which I gave just now is related to the problem which we did earlier. I have a matrix A which is equal to 0, 1, 1, 0. What are the eigenvalues of this matrix? Eigenvalues of this matrix, I must write A minus lambda I is equal to 0. Determinant is equal to 0. That means determinant of minus lambda 1, 1 minus lambda is equal to 0. It implies lambda square minus 1 is equal to 0. You have two eigenvalues, lambda is equal to 1 and lambda is equal to minus 1. Lambda is equal to 1 and lambda is equal to minus 1. Now, if you want to find out the eigenvectors, A acting on some xy will be equal to plus 1 into xy. This is the xy is the eigenvector corresponding to eigenvalue plus 1. But what is A? A is 0, 1, 1, 0. So what will be right hand side? Yx is equal to xy. This implies you will get x is equal to y. You cannot get the unique vector, you only get a relation between x and y. Which means this eigenvector b1 is equal to x, y is equal to x. Okay, this is the eigenvector, which means the direction is like a diagonal. 1, 1, 2, 2, 3, 3, 4, 4, any of them is an eigenvector for this. But we can always choose a normalized eigenvector. That means we choose a unit vector along that direction. Normalized eigenvector. So I will write b1 as 1, this divided by 2x square. So which gives you 1 by root 2 into 1 1. So you can see this is the eigenvector, this is the vector which I have taken in the previous example. So I am choosing an example such that I can borrow some results from the previous example. And if I ask what is the eigenvector corresponding to minus 1, that means 0, 1, 1, 0, xy is equal to minus 1 xy. So this gives you yx is equal to minus x minus y. This gives you x is equal to minus y. So my new vector, that is my b2, is equal to x minus x divided by 1 by square root of 2x square. This is equal to 1 by root 2 into 1 minus 1. So the basis that I have already written down earlier is like this. Previously also I had this basis. Remember A1, A2 was 1, 0, 0, 1 and B1, B2 was 1, 1, 1 minus 1 with the square.
Is it same as 1 by root 2 minus 1, 1?
Yeah, it is also same as minus 1 and 1. And this one and minus 1 and 1 are linearly dependent. It's minus of that. So you can use this or that. But once you make one choice, consistently use the same thing. So in between the calculations, you should not switch. But you could have chosen minus 1, 1 or 1 minus 1. Okay, so now we know that if you have, we know that the transformation matrix. So here you have to do one thing is that when I gave you this matrix A is equal to 0, 1, 1, 0. Okay, nobody told me what is the basis in which this matrix is of this shape. Okay. If nothing is given, you can assume that this is, there is no loss of generality if you assume that this is the matrix in the trivial basis. Trivial basis is 1, 0, 0, 1. Correct? So, without any loss of generality, we can assume the basis in which A is 0, 1, 1, 0 to be a basis. That means basis is given by 1, 0, 0, 1. Now we know in the previous case the transformation from this basis to that basis. Correct? So from previous problem, we know that this B1, B2 can be written as S times A1, A2, where A1 is the trivial basis and S is equal to 1 over 2 times 1, 1, 1 minus 1. Now if you look at this structure, that it is like the eigenvector B1 is kept in the first column, eigenvector B2 is kept in the second column. So the columns of this transformation matrix is eigenvectors of the matrix A. So you can immediately write down, so in this case it turns out S inverse is also same as 1, 1, 1 minus 1, and then ask what is S inverse A S, that is equal to 1 by 2 into 1, 1, 1 minus 1, 0, 1, 1, 0, 1, 1, 1 minus 1, that is equal to 1 by 2, 1, 1, 1 minus 1, and I have 1 minus 1, 1, 1, so that is equal to half 2, 0, 0 minus 1. So which gives you 1, 0, 0 minus 1. 1, 0, 0 minus 1 is the diagonal matrix, where along the diagonal you have eigenvalues. 1 and minus 1 are the eigenvalues. Correct? Now if I want to calculate the square root of this matrix, all that I have to do is so square root of 0, 1, 1, 0 to the power half is S 1, 0, 0 minus 1 to the power half with S inverse. Okay. Now what is this? This is equal to 1 by 2 into 1, 1, 1 minus 1. The square root of this one is 1, 0, 0 I into 1, 1, 1 minus 1. So that gives rise to 1 over 2 into 1, 1, 1 minus 1. This is 1, 1 I minus I. So that gives you 1 by 2 times 1 plus I, 1 minus I, 1 minus I, 1 plus I. So this is the matrix that corresponds to square root of. So this is not only true for this particular operation, you can also do this for any
So you said that in justified always how maybe a given matrix is with respect to some non-trivial basis. How do we know that?
Yeah, so if you know, see, to know what is the basis with respect to this matrix is this, you should know at least what with respect to one basis. Okay? So, why I said it is without any loss of generality is that supposing you have a basis, this may be some other basis, but you can rotate that basis to this basis, and then you can say that because you don't have any other information, so you can say that this matrix is with respect to this basis, and then only then the transformation matrix to eigenvectors will come placing eigenvectors along the column. Only under that assumption.
Okay, that can be proved. That can be analytically shown also.
Yeah, you can argue that in a simple way like this.
That is, each column of the similarity matrix, transformation matrix should be
Correct. Yes. That is, if you say you have an eigenvector v1, sorry, v1 in this case is equal to 1 by root 2, 1, 1. This is essentially means that this is equal to 1 by root 2 times a1 plus a2. Correct? Because this is, I'm taking a trivial basis, I can write it like this. I can interpret these things as the coefficient of this. Correct? So then the transformation matrix will be these eigenvectors along first column, second column.
You are assuming that A1 and A2 are
Trivial basis. Only if we assume that it's a trivial basis, then the transformation matrix is same as the matrix with which eigenvectors are placed along the column. But this assumption is, there is no loss of generality in this assumption because they have not given the basis. So whatever is the basis in which this matrix has this elements, you can label that basis as trivial basis. Because if that is not trivial basis, you should have some reason to believe that it's not trivial basis. Then they give only matrix element, you have no reason to believe. So you can always label that as a trivial basis. Since your starting point is the given matrix, no loss of generality if you call that matrix is in this shape because of the trivial basis. But if you know that trivial basis gives you some other matrix element, that means such an information should be available. If it's available, then this will be a different basis, but you can always make a transformation from that basis to this basis using another transformation matrix, and this matrix will be kind of a product of those two transformation matrices. So I don't think there is any loss of generality even in that case. So this is a basic general similarity transformation procedure or diagonalization procedure. Now you ask the question that can we always diagonalize a matrix? Every square matrix you cannot diagonalize always, but there are some class of matrices that can be always diagonalized. For example, normal matrices can always be diagonalized. Normal matrices assure you that you will have a set of linearly independent eigenvectors. If you have an n by n matrix, n by n normal matrix, you will have n linearly independent eigenvectors. Okay, now these n linearly independent eigenvectors can be orthogonalized using Gram-Schmidt orthogonalization procedure. Using this basis, you can diagonalize the matrix. But if you have a general square matrix, if there exists n linearly independent eigenvectors, which is not guaranteed for a general square matrix, if there exist n linearly independent eigenvectors, then it can be diagonalized. Otherwise, it cannot be diagonalized. Such matrices which cannot be diagonalized are called defective matrices. So when I say defective matrix, it means non-diagonalizable matrix. That means the number of eigenvectors that are linearly independent is less than n, the size of the matrix.